Pineapple.
Ah, okay, cool. No one raised a hand. I should have said all the secrets before it was on. Oh, sure. Okay, I can go back and do a quick recap. So, okay. Hi, I'm here to talk about Meraki devices. Who are Meraki? They were founded in 2006, bought by Cisco in 2012. They sell SMB networking stuff. Their business model is we sell you a cloud, you manage your stuff, you don't have to do NAT. They deprecate stuff, you buy new stuff, sales is happy, line goes up. Want to manage it yourself? No, too bad you can't. TLDR, this is late-stage capitalism. If you want to buy a used one, make sure it's unclaimed. I bought one because I was cheap. They insulted me by not giving me the source code. And we're back. So U-boot also does other things. It can do DRAM training. It can initialize I/O. Usually it loads from other storage. And it's really cool because it includes a very simple command line. And I say conceptually similar to BIOS and UEFI. It's not really, because BIOS and UEFI actually have some de facto standards and U-boot doesn't, but simplification. Bear with me. So where is UART in this device? I'm going to save you pointing. It's there. That's the UART header on this device. Meraki devices usually include a UART header. It may or may not be populated with pins, and it may or may not be labeled. This is the UART header on another device, which was pre-populated with pins. But this is really useful because it gets us the output of the device when it's booting. This is kind of step 0 in terms of figuring out what the device is doing. So before I go any further about my research, reverse engineering resources. So U-boot is GPL licensed, as is Linux and BusyBox and a lot of other things that run on these devices. But Meraki take 12 months or more on average to provide source code after you request it. But the NAND on their devices is unencrypted. And AliExpress will sell you a dumping device for about 60 euros. So in case Meraki are not forthcoming with the source code, you can always do the hard way and just dump NAND and get a copy there because NAND is unencrypted. So the target devices that I'm going to start with are all 802.11ac or LTE gateways. This would be the Z3 wired router here. So this is meant for teleworking. So your company wants to have a secure VPN in your home office. They'll ship you a Z3. You plug that in, and you're on the company's VPN. And the cellular gateway is kind of the same thing. That's more like a backhaul thing. So if you have a remote office and you want to have, a centrally managed LTE connection, you can do that through the cellular gateway. So common bootloader weaknesses, you heard in the previous talk about JTAG and serial and getting access to a device this way. I'm going to go a bit more into detail here. So the 3 main ways are you can interrupt boot and get a prompt. That's like super easy. You plug in serial, you control C, you get a prompt in U-boot, and you can basically load your own kernel, set the command line, you're God. The other way, this is something that was presented recently at, I believe, Black Hat, was a Sonos device had the environment stored in U-boot, but it also sourced it from Flash if it was present on Flash. It wasn't in the production device, but the researchers placed an environment in Flash, which U-boot then read, and they could modify the boot flow that way. The other way that you can always do it is you can ask the vendor for the source code for the bootloader, compile it yourself, flash it to the device, and that's one way to gain persistence on the device. So here's a table. We're going to come back to this. So do we have bootloader command line? If we look at the source code for the Z3 U-boot, yes, the command line is enabled, the hush parser is enabled, so sweet, there's a command line. What about Autoboot? Yes, there is Autoboot, but there's an Autoboot stop string X, Y, Z, Z, Y. So if you put it X, Y, Z, Z, Y during boot, you can interrupt the Autoboot and get into U-boot. So good news. But there's no boot delay. So they've disabled the ability to put in that Autoboot string. And so even if you sit there with a Python script or C or whatever language goes faster than C, spitting out X, Y, Z, Z, Y on the serial, you won't get a shell because they've disabled boot delay. So this is actually an evolution for them on devices, and U-boot builds before 2017. It was possible to interrupt boot just by doing X, Y, Z, Z, Y. But after 2017, which is most devices because they auto-update their firmware and bootloader, they've removed the boot delay, so you can no longer just interrupt boot and get a shell. What about the environment? Well, unlike the Sonos device, unfortunately, Meraki have done their homework here, and config environment is nowhere. So the environment is compiled into U-boot. There's no possibility to modify this. It doesn't check anywhere on Flash. My disappointment is immeasurable, and my day was ruined. So here's a summary of our current situation. Boot delay has been removed, so there's no easy way to break into the command line. We can't modify the environment or place one on flash because it's compiled into U-boot. But what about recompiling and overwriting the bootloader? Is that still a possibility for us? Well, no, because they're using secure boot, as you can see here in the output from the bootloader. So no, we can't recompile and overwrite the bootloader because the bootloader is presumably signed and checked. I'm going to talk a bit about secure boot here. So we're probably familiar with how it works on PCs. Embedded devices are very similar. So in embedded devices, what you typically do is you typically burn a certificate into some one-time programmable fuses, and this is the hash of the certificate that's used to sign the boot stages. In this case, U-boot, if it's configured to verify images, will then also verify the signature of an image that it loads. And so you can't manipulate the bootloader because that's signed and checked by the boot ROM inside the SoC, which is burned in the SoC. You can't modify that. You can't install your own key, typically. And U-boot will go and verify the operating system image that you're trying to load. So you can't manipulate that either because U-boot is checking signatures, and if the signature of the operating system image doesn't match what the hash of the certificate is, then it's not going to boot. Interesting note, verify is a U-boot environment variable that you can use to control whether U-boot will verify the payload or not. Unfortunately, if it's unset in the environment, U-boot defaults to validating signatures. So that's not an option here either because, of course, the environment is compiled in. But something to remember if you're ever looking at a device that has secure boot. And vendors use U-boot's verified boot. Right? Well, here we have boot command run Meraki boot. And here we see Meraki boot Meraki QCA. And up here we have boot sign part. So we're going to load the image, we're going to validate it, and then only if it validates that and clause, then we're going to boot it. If validation fails, then we won't do anything. So everything in the blue is signed and checked by the SoC on boot. So this is Qualcomm specific, but primary bootloader and secondary bootloader, and then U-boot. The boot Meraki QCA function does several things inside. It checks if secure boot is enabled, and if it's not, it burns the certificate hash into the fuses and forces secure boot to be on. Then it will boot the diagnostic image, which again is signed, so we can't replace the diagnostic image with our own and boot that. As part of Meraki's upgrade process, it will check if there's a part.new, and if it is, it will then copy that and boot it. If a node-specific unlock exists, so this is for Meraki developers, it will chain load their own U-boot build. Finally, it will run boot sign part, which we saw on the previous slide here, which will validate the signature. And if those fail, it will reset the device. So there's no obvious security flaws here in this flow. Everything here is signed, it's checked, and if the signatures fail, the device will reset. Except there was something that I excluded on that diagram for dramatic effect, and that is here, from the source code and from Ghidra, there are some Meraki boards that don't support secure boot. So the first, actually the 0th condition in here before it checks and forces secure boot on is if I am on one of these devices, skip enabling secure boot and skip signature validation. Okay, that's interesting. So what's this product ID? Well, these are a list of Meraki devices. They're all running the same bootloader. They're all the same Qualcomm platform. And some of these have secure boot and some of them don't. Okay, interesting. Maybe there's something we can do here. Where's the product ID stored? Well, if you look down here with these arrows, which I'm so thankful it comes across on the projector, that's an I2C EEPROM. So the product ID is sourced from an I2C EEPROM. Okay, also interesting. So 24 hex is the product ID of this product. What if we just modified that to something that doesn't have secure boot? Well, if we do that, we find that instead of having secure boot enabled and loading a kernel from a fit image and then validating the signature and checking it, well, now we get a different output. We see wrong image format for boot M command, can't get kernel image, resetting. Okay, so that's certainly different to what we saw before. So basically, from this flowchart here, we check the product model, and if it happens to be something that should have secure boot, then we load it and we verify the signature and we boot it. And if it happens to be something that doesn't have secure boot, then we no longer verify the signature of the image. Okay, so what's the situation here? Well, secure boot is enabled, the boot chain is signed, but we have a signed U-boot build that will boot unsigned images if it happens to think it's running on a product that doesn't have secure boot. The product ID is stored in an external EEPROM that doesn't have any encryption, doesn't have any signature, and you can just modify it. So you just change 1 byte in this EEPROM, and you can tell the device, hey, you're now something that doesn't have secure boot, so you shouldn't verify the integrity of your payload. Now, there are actually 2 copies of this information in the EEPROM in devices manufactured after 2017. And the only thing that I can tell that they've done here is have a second copy in case the first one gets corrupted, but actually only their firmware checks that, not even the bootloader. So if you change it, even in the first one, U-boot will just happily read that and go, great, I'm running on a device that doesn't have secure boot. I will now boot whatever you want without validation. So what we can do with this is we compile U-boot from the source code that Meraki provided. We put it into a fit image, a flattened device tree image. We put it into what would normally be the firmware partition, which U-boot will now boot without verification, and we now have an unlocked copy of U-boot that we boot on the device. And then we can TFTP boot, we can boot whatever we want. So we're done. We have unsigned code execution on the device. Can Meraki patch it? Well, on these devices, because they are 7 to 8 years old, they have some with secure boot and some without. U-boot builds after 2019 removed support for devices that don't have secure boot, so they've closed the hole, right? Well, multiple devices use the same signing certificate. They didn't use signing certificates per device. It's across the entire family, and there's no rollback protection. So what we can do is just flash an older U-boot build onto the device that contains the vulnerability, and so even devices manufactured after 2017, you just flash the old version of U-boot on it, which is still signed, the secure boot chain is still intact, and you can boot unsigned payloads. So the Z3, the Z3C, and the MG21 are vulnerable to this. The MG41 is not, because it uses a different type of flash, and they had to rewrite that function, and they inadvertently removed the bug. So we're going to look at Meraki Go. Meraki Go is Meraki, but cheaper. You don't have the dashboard. Everything's managed through an app. You can think of it as just the core. Quick side note, Meraki decided that Meraki Go doesn't make them enough money, so they're actually going to discontinue it and focus solely on their cache printing exercise, which is normal Meraki devices. But that doesn't mean you can't buy Meraki Go devices and look at them. So we're looking at an AP, the GR10, and a wired router, the GX20. Does it work? Well, if we make the same modification to the EEPROM on the GX20, we find that it doesn't work. It's still verifying the hash integrity because the code path doesn't exist in this U-boot release. But everything's signed with the same cert. So just flash U-boot from the Meraki device, and you have the same vulnerability again. Change the EEPROM value, and you boot an unsigned payload. It's great. It's the gift that keeps on giving. So the GX20, which is just a Z3 without the wireless radios, and the GR10, which is really an MR20, are vulnerable. The GX50 is actually not Qualcomm-based, so it's not vulnerable to this, and the GR60 is probably vulnerable, but mine hasn't arrived from eBay yet, so maybe you'll see me at Chaos Congress in December. But that's all old news. These are old products. They're 7, 8 years old. Let's look at their current products. Their MR36, which is a Wi-Fi 6 AP. Well, I don't have the source code to show you because Meraki haven't provided it, but if we throw U-boot into Ghidra, we can see we have the same thing. If the product number is below 16, don't do secure boot. So does it work? Yes, it does. You can change it. It doesn't validate the image anymore, and you get unsigned code execution. I can only imagine this is a mistake on their part because none of their current gen devices ship without secure boot. So don't know how this snuck in, but great for me. So the MR36 is definitely vulnerable because I have one on my desk at home that I can boot unsigned code on. The MR44, 46, and 56 are probably also vulnerable. I don't have them because they're still quite expensive, but they use the same U-boot release, so it should apply. Now, let's talk a little bit less tech. Devices supporting bootloader unlocking. Meraki has zero incentive to do this, but they could. It's right there. If node-specific unlock exists, chain load U-boot. They could offer you the ability to unlock your device and run an alternative firmware on it. Do I expect them to? No. Should they be required to? It's a question for regulatory bodies and right to repair. My personal opinion is yes, but if I were an MBA, I'd probably say no. But I want to tell you steps that you can take to ship a secure device if you want to. In production devices, you should disable the command line of the bootloader so that users like me can't get in and do stuff with that. I talked earlier about the string XYZZY, which in pre-2017 releases would get you a shell in the bootloader. U-boot offers an option called Autoboot encryption, where instead of providing the actual password to interrupt boot, you provide a SHA-256 sum of the string. This is very hard for someone to reverse. You'd have to have a SHA-256 collision to figure out what the string is. So if you're going to ship a device and you want to have the ability to interrupt boot, use Autoboot encryption in your bootloader so that people can't just strings the dump and see what it is. Compile your environment into U-boot. Meraki, you're doing this. You want config environment is nowhere so that someone can't put it on flash and interrupt or change your boot flow. And use anti-rollback features. They exist. They're supported. And it means that you can't take an older vulnerable version of the bootloader and flash it on the device to exploit a bug that's already been fixed. And this is not specific to Meraki because they're not using encryption on their devices, but in my previous work with some Fujitsu BMCs, don't ship encryption keys in your firmware. It's a bad idea. Again, you can just strings it or throw it into Ghidra or IDA and get the encryption parameters out and then use that to decrypt things. So there's secure places to store these things like an enclave or trust zone inside the SOC that make it a lot harder for an attacker to extract. My appeal to you as people who work in businesses, ask your vendor for GPL source code. Require it as something your procurement department does. It takes them 5 minutes to write an email. Vendors don't expect to be asked for their source code. A lot of them are unprepared to provide it. Source code is a lot easier to scan for vulnerabilities than a binary is, and your vendor might not even have the source code. I'm dealing with a large ISP right now, not from this country, but one nearby, who subcontract the firmware of their endpoint devices. So think the wireless router that's running in your home. They don't even have it. When I asked them for the source code, they said, oh, we're going to have to go back to our vendor and get it. And then they gave me a source code blob that doesn't compile and is missing a config. And I said, hey, this doesn't work. And they said, oh, news to us. We never tried. Maybe you want to. And if your vendor won't comply with the GPL license, what other things are they infringing upon? This is a great test to see if your vendor's got all their things in order or not. So you're listening to this talk, and probably someone from Cisco is watching it on YouTube later and wondering, why didn't I responsibly disclose this to them? Well, Meraki have a bug bounty. But there are issues with it. BugCrowd, the platform that they use, have been in the news for some controversies, and I happen to know some other researchers who have reported issues and not received a payout. Their maximum payout for the bug bounty program is $10,000, which, in my opinion, avoiding e-waste from these devices is far more valuable. Additionally, participation in their bug bounty requires signing an NDA. Not only do you affirm that you won't talk about it now, they also reserve the right to seek damages from you if you should ever break the NDA in the future. And I'm sorry, but this is not a bug bounty program. This is not a vulnerability program. This is brand image protection from the marketing department. This is not openness and transparency that you want from a vendor that talks so highly about security. Additionally, the things that I've discovered are probably deemed not in scope. These are direct quotes from their bug bounty program. So deficiencies in a security feature for an on-prem product. I would call this an on-prem product. Any attack which renders the device permanently inoperable. Well, if you change the byte in the EEPROM, it won't boot their firmware anymore. And if it won't boot their firmware, it won't update. It won't route packets. It won't generate an Wi-Fi AP. So it's probably considered permanently inoperable from their point of view because it won't run their money-generating code anymore. Any vulnerability not present in the most recent beta firmware of the product. Well, of course, they fixed the bug in the bootloader, but you can just roll back the bootloader. Therefore, sorry, no money. Any hardware bugs which require a debugger to recreate. So I have to flash these or desolder because I don't have a remote code execution vulnerability for Meraki devices. If you did, you could do this all in software. You can just manipulate the EEPROM and overwrite things in NAND. I only do this because I don't have the keys to the kingdom. Finally, I want to talk about GPL compliance. It's not good. they don't have a written offer for source code with their products. They don't have any documented way to request the GPL source code, and requests take years to process. So if you have contributed to any of these, please get in touch with me after the talk or some other time during the day so that we can talk about what our options are, because I'm kind of tired of waiting. You may remember me from such talks as defeating planned obsolescence for Cisco Meraki switches. This is a talk I gave at Chaos Camp last summer. I mentioned that I maintain a firmware for older Meraki switches. So if you happen to have one or know of someone who's going to throw one away, it is possible to run another firmware on them and still use them as a switch. You won't have cloud management, but I actually consider that a plus. Thank you. I want to thank OrangeCon for providing me a platform for this. I want to thank you all for now holding your vendors accountable for the software licenses they use in their product and requesting source code from them. And if you happen to plan on shipping a secure device, thank you for considering user freedom. So allow your users to securely unlock their devices should they wish to put an alternative firmware on it after the end of life or something. So thank you so much for your time today. And I think we have a little bit of time for questions. If you have any, I'm happy to answer them. Thank you.
Well, thank you very much for this brilliant talk. Is there anyone with a question in the audience?
Hi. I'm a student. I just have a simple question. How did you know hardware part which stores the product key? Was it written somewhere?
So I have a little bit of a hardware background, but the easiest way is just by looking at the PCB and typing in chip names. So I knew from the source code that it referenced an I2C EEPROM to get that information. And there was only one on the board that actually looked like it would hold the data. So it was a pretty clear candidate to dump.
I see. Thank you.
Any other questions? Well, if there are no further questions, I would like to offer you a token of our appreciation here at OrangeCon. Thank you very much.
Thank you all for coming.
Round of applause, please.